technology and product leader with over 14 years of global experience spanning software development, AI driven systems, robotics enabled platforms, and enterprise scale digital transformations. Currently serving as a software development manager at Amazon, he leads cross functional teams building next generation internal platforms that power enterprise procurement, contract intelligence, and data driven decision making at scales. His work directly supports over 1,50,000 employees globally and has enabled more than 100 million USD in projected annual savings through AI assisted analytics and platform modernization. Mr. Darshan holds a Master of Science in Electrical and Electronics Engineering from Penn State University, USA, and a bachelor's degree in Electrical Electronics Engineering from Shivaji University, India. His academic foundation is strongly complemented by extensive industrial exposures across globally renowned organizations such as Amazon, IBA, Star Key Hearings Technologies, L&T Infotech. His professional journey uniquely bridges deep engineering foundations with real world system design, spanning embedded firmware, robotic adjunct systems, machine learning driven analytics, and large scale SAS platforms. Prior to Amazon, he played a key role in healthcare technology, medical robotics softwares, and industrial analytics platform developed globally. He is also known for translating complex technical ideas into practical, high impact solutions. He is frequently invited by senior leaderships to drive strategy alignment, mentor emerging leaders, and guide interdisciplinary teams through complex problem spaces. His work reflects a strong belief that the future of engineering lies not just in algorithms or hardwares, but in thoughtful system design, ethical intelligence, and human centered innovations. We are honored to have him as a resource speaker for this faculty development program, and I look forward to an enriching and inspiring session. So, once again, welcome, Mr. Darshan. Now, I request you to start with the station. Thank you.
Thank you, sir. I appreciate that intro. And I'll start with my presentation. Okay. Is the presentation live for everyone?
Yes, yes,
Yes,
yes.
sir.
Yes, sir.
It's
Okay,
visible. You can continue, sir.
perfect. Thank you, sir. So, good afternoon, everyone, and thank you to the Institute, the Electrical Engineering Department, the AICTE ATAL Academy for inviting me to be a part of today's program. By a brief way of introduction, my background, as Sir already pointed out, has been in software, embedded engineering, AI, ML related projects, and overall large scale system integration. AI and machine learning systems today overlap along with robotics and embedded engineering. They go hand in hand. I've actually had the opportunity to work on small scale and large scale real world systems that operate continuously and at significant scale. That perspective alone shapes how you think about AI. It's not an abstract concept, but as something that lives inside complex engineering systems with real constraints and real consequences. So, when we talk about artificial intelligence and machine learning today, the conversation often begins with powerful technologies and rapid innovation. In this session, I want to explore how that influence is taking shape in a very tangible way, in how we move, how we consume energy, how cities operate, and how everyday engineering decisions are increasingly guided by intelligent systems. Today's discussion focuses on how AI and ML are shaping the future of mobility and daily life, particularly through sustainable electric vehicles, smart mobility systems, and infrastructure. And much of this intelligence works quietly in the background, continuously optimizing performance, safety, and efficiency across interconnected systems. I'll then begin with a real industry example to ground this discussion in practical reality, and I'll connect it through Amazon's case study. From there, we will expand the same ideas across mobility, electric vehicles, infrastructure, and urban systems, focusing on system behavior, real world impact, and future direction. This topic is relevant today as engineering systems become more intelligent, more connected, and more central to sustainability goals. For educators, engineers, and students, understanding how the systems behave, where the overlap lies, and what hybrid approach everyone needs to follow is where I see a lot of interest in currently, and how responsibility, safety, and governance are embedded within them. My perspective comes from seeing how the systems behave when they run continuously at scale and with real world constraints. With that context, let's look at how we'll structure this conversation. So, the agenda for today, let me briefly outline how we'll approach this discussion today. I'll begin with a short AI ML primer so that we are all aligned and we have a common baseline. This will help align perspectives across different backgrounds and ensure that examples we discuss later are easy to follow. From there, I'll walk through one real industry case study, um, which I would link with Amazon as my current company. The purpose of this example is not to focus on specific company, but to highlight the patterns that are used in machine learning and when we use it at scale, how the intelligent systems behave, how decisions are coordinated, and how learning happens in real operational environments. Once we have that concrete example, we'll generalize the same idea across mobility systems, electrical vehicles, energy grids, and smart cities. You'll see that while the domains change, the underlying intelligence patterns remain remarkably similar. Finally, we'll bring the discussion together by looking at governance, security, and responsible AI. In mobility and energy systems, these are not optional considerations. These are engineering requirements that directly affect safety, trust, and long-term adoption. Throughout the session, I encourage you to think about how these ideas relate to your own teaching, research, or areas of interest. And we'll definitely do a Q&A session, and I'll be open to ideas and discussions. With that roadmap in mind, let's start by building a shared understanding of what we mean by AI and ML in practice. Before we go any further, it's important that we clearly align on terminologies because these terms are often used interchangeably in everyday conversations. So, what do we mean by AI and ML, artificial intelligence and machine learning? So, artificial intelligence is the broader goal. It refers to making machines capable of intelligent behavior. That intelligence typically involves three things: perceiving information from the environment, making decisions based on that information, and then taking appropriate action. Machine learning is one of the most common ways we achieve this today. Instead of writing fixed rules for every possible situation, machine learning systems learn patterns from data. That's how we drive the learning. AI is an umbrella term, right? It encompasses ML, computer vision, and the other subset that come under it. While machine learning is just a subset using algorithms to learn from data. For instance, just as a side tangent, when we mention deep learning, it's a type of machine learning that uses neural networks, power images, and power image recognition in autonomous vehicles. So, machine learning is currently the dominant approach to artificial intelligence. As they see more data, their behavior improves. This distinction matters because in real engineering systems, AI is not just a model running in isolation. It is an end-to-end system that senses real world, processes information, learns from experience, and responds accordingly. If we compare this with traditional software, the difference becomes clear. Traditional software behaves exactly as programmed. When conditions change beyond what was anticipated, the system often breaks or produces incorrect results. Machine learning systems, on the other hand, adapt. They would write their own set of rules, they would write their own set of code, and then they would bypass what error or what obstacle they hit. That is how machine learning evolves. They improve as they encounter new situations and examples. So, in practice, real world AI systems combine both of these approaches. There are always rules, safety checks, and logical constraints. The learning components sit alongside these rules to allow the system to adapt to these changing conditions. This balance is especially important in domains like mobility and energy, where environments are dynamic and uncertainty is unavoidable. Another important point is that AI systems do not make one time decisions, they continuously operate in a loop. Data comes in from real world through sensors, devices, or user interactions. Models learn patterns from that data and decisions are made. Outcomes are observed. That feedback is then used to improve future decisions. This continuous learning loop is what makes AI powerful. At the same time, I do want to touch on one of the biggest pain points, and that is governance, safety, and oversight, because of how these systems are integrated in day to day activities today. So, when systems learn and adapt over time, we definitely should ensure they do so in ways that remain safe, predictable, and aligned with human intent. This loop will quietly reappear in every example we discuss today. With that foundation in place, let's look at how these ideas show up in real world industry systems operating at scale. So, what you see on this slide is the simplest and most important mental model for understanding AI in real systems. At, it, at its core, AI operates in a loop. The system observes the real world, collects the data, learns patterns from that data, makes decisions, takes action, and then observes the outcome. That feedback flows back into the system and influences future decisions. This loop runs continuously. Data in goes through a learning algorithm, goes through a model, and goes through predictions. And this will operate continuously. For example, in car, artificial intelligence would come from sensors, autonomous drive algorithms, while infrastructure AI would come from signals, routing. So here, machine learning is relevant. If you compare mobility, enormous sensor data from devices like LiDAR, traffic cameras come in and demand machine learning methods. They don't need handcrafted rules. They have to continuously keep learning. And this learning is, I'm going to touch briefly on this. It's divided into three parts. First one is supervised learning. Second is reinforcement learning, where the feedback from success or failure flows back. And then there is unsupervised learning, which is finding patterns and the highest level of machine learning that's incorporated in mobility today. What's important to recognize is that this loop is not specific to one industry or one technology. The same loop appears across many domains. You see it in warehouses coordinating robots, in vehicles monitoring performance and surroundings, in traffic systems managing flow, in smart homes optimizing energy use, and in power grids balancing supply and demand. If we look at electric vehicles, this loop shows up very clearly. The artificial intelligence systems predict battery health, estimate remaining range, optimize energy use based on driving behavior and environmental conditions. Every drive generates feedback that improves future predictions. In traffic systems, the same loop predicts congestion. Data from sensors and vehicles feeds models that anticipate bottlenecks before they form. So decisions are made to adjust signals or reroute traffic, and the outcomes feed back again into the system. Comparing this with smart grids, AI predicts energy demand and renewable generation. That prediction would allow the grid to balance load, avoid peaks, and integrate electrical vehicles more effectively. Across all these examples, the technology changes, but the intelligence pattern remains the same. It's like coding where you see different languages are used, but the underlying algorithm would remain the same. So, data, learning, decisions, action, and feedback form a continuous cycle. This is why AI is so powerful in mobility and sustainability. It allows system to anticipate and optimize rather than simply react. I wanted to cite a couple of examples that you guys may be aware of. Tesla is one of the new companies in that came out with autopilot that uses neural nets to interpret this camera data for steering decisions. It would change lanes, it would reroute, it would go through traffic signals. And another example would be Waymo's, which is a Google's subsidiary company. Their fleet aggregates this sensor data to update high definition maps in the given boundaries that they operate. These are real world AI in mobility instances. I wanted to briefly touch how AI connects through mobility and sustainability. So, with that foundation in place, let's look at a real industry example where this loop operates at scale and then generalize across different sectors and how it affects the daily life. So I wanted to ask a general question, address a general question. Why AI and ML for mobility? When we talk about mobility today, we are no longer talking only about vehicles or roads. We are talking about interconnected systems, vehicles, users, infrastructure, energy, and cities, all interconnecting in real time. The question is not whether mobility will become more intelligent, but how that intelligence will be designed, governed, and applied. So, in the next few slides, we'll unpack why AI and ML have become such a natural fit for mobility systems, how they enable prediction, coordination, and optimization at scale that traditional approaches struggle to handle. So, let's look at the key reasons why mobility systems increasingly rely on AI and ML. So, modern vehicles, infrastructure, and cities generate an enormous amount of data. Sensors inside vehicles, GPS signals, cameras, charging stations, and traffic systems continuously produce information about movement, energy use, and environmental conditions. At the same time, advances in computing, cloud platforms, edge devices, high speed connectivity like Internet of Things and 5G make it possible to process this data in near real time. This combination of data availability and computational capability is what enables entirely new kinds of solutions. Many of the challenges we face in mobility today are inherently complex. For example, traffic congestion is not just about volume, but about timing, coordination, and human behavior. Similarly, battery optimization depends on driving patterns, temperature, charging habits, and degradation over time. So, safety involves anticipating rare but this critical events. These are the problems where static rules struggle and where AI driven intelligence becomes valuable as it's near real time. Large industry surveys consistently show that organizations expect AI to fundamentally reshape how systems operate over the coming decade. This reflects a broader recognition that intelligent, data driven systems are becoming central to competitiveness, efficiency, and sustainability. The underlying goal here is not automation for its own sake. The goal is to improve efficiency, enhance safety, and support sustainability by enabling these systems that can predict, adapt, and coordinate intelligently. One of the quick citations I wanted to give was 86% of global employers around the world have already made a statement that AI will transform their businesses by 2030. To make this more tangible, imagine a typical commute in the near future. You wake up and your electric vehicle selects an optimal route based on current traffic and energy conditions. Traffic signals then adapt in real time to keep vehicles flowing smoothly rather than stopping unnecessarily. Your vehicle charges at home using solar power when energy is cheapest and cleanest. An AI driven assistant quietly manages timing, reminders, and coordination in the background. This is not distant vision. Elements of this already exist today in different forms. And just to cite, a lot of those parts are being used in different countries in different forms. The key point here is that AI acts as the connective tissue, linking data, decisions, and outcomes across the entire mobility ecosystem. In the next section, we'll move from this vision to a real industry system where these ideas will pan out at scale. So, a useful way to understand this in practice is to look at coordination and mobility where they already happen. So, warehouse logistics face problems similar to city traffic, similar to mobility, similar to infrastructure. There are dense flows, there are collisions, and there are complex integrations that happen in real time. We will see how Amazon uses AI to coordinate its warehouse traffic. Let's now ground everything we have discussed in one real world example. Warehouses by nature are physically demanding and are one of the most constrained, safety critical environments to automate. The work is repetitive, requires long hours of walking, lifting, and carries safety risks when done at scale. As order volume increases, these challenges grow rapidly. The introduction of robots in fulfillment centers was not about replacing people. And this point needs to be reiterated. It was about changing the nature of the work. And this will connect to AI related any job that would stew in. Robots take on the most repetitive and physically exhausting tasks, allowing human workers to focus on activities that require judgment, flexibility, and oversight. This is where AI plays a critical role. AI is responsible for coordinating millions of small decisions every day, deciding where inventory should move, which robot should move first, how congestion is avoided, and how work is balanced across the system. These are decisions that humans simply cannot make reliably or fast enough at this scale. What makes this example especially relevant is that The same intelligence pattern appears in other domains, as I had pointed in the previous slide. Coordinating robots in a warehouse is fundamentally similar to coordinating vehicles in a fleet or a traffic in a city. The environments differ, but the decision-making challenges are remarkably similar. If we break this down, the problem at hand that AI solves here is the first challenge of scale. Thousands of orders are processed per minute through Amazon and through their fulfillment centers. Number two is role of artificial intelligence, which uses vision and routing algorithms to route that traffic to the proper warehouses, proper allocator, and proper logistical department. And number three is the outcome, which deals with efficiency, fewer injuries, and how much a human spends time on a repetitive task. So, over the next few slides, we'll unpack this case study and then connect this to mobility and our daily life. So, why Amazon is a relevant AI case study? Amazon, particularly, is powerful for using AI because it challenges the fundamental problems of scale. When you operate at level of millions of products, thousands of facilities, and highly variable global demand, manual decisions are simply not at scale or at par. Even well-designed processes and experienced teams reach a point where this volume and speed of decisions exceed human capability. In this environment, the challenge is not intelligence at the individual level, but coordination at the system level. Decisions must be made continuously, in real time, and across many interconnected components. That is why Amazon uses AI. Not because it is fashionable and not because it's experimental currently, but because it is at this scale. Sorry. So intelligent coordination becomes impossible without it. AI enables millions of small decisions to be made consistently, safely, and efficiently, second after second, and in a loop. This is also important to be clear that what AI is doing here, it is not replacing people. It is enabling that coordination in areas where humans cannot manually decide fast enough or consistently enough. Human judgment, oversight, and responsibility still remain essential. This same principle applies directly to mobility systems. Electric vehicle fleets, traffic networks, and smart cities face similar challenges. There are large number of moving components, constantly changing conditions, and the need for real-time decisions. So as scale increases, coordination becomes the primary problem and AI becomes a practical necessity. So as we go through this case study, keep that lens in mind. We are not studying Amazon as a company. We are studying how intelligent systems behave when scale forces new ways of thinking. Let's now look at what scale actually means inside a fulfillment sensors center. Sorry, excuse me. So today, Amazon has deployed over 1 million robots across its fulfillment centers globally. What's important to understand is these robots are not operating in isolation. They work directly alongside hundreds of thousands of human associates every single day. In this environment, AI plays a coordination role. It decides where robots move, when inventory is brought to the workers, how tasks are sequenced, and how congestion is avoided across the facility. Millions of movements are coordinated every day across facilities, something that would be impossible to manage manually. So, one of the most immediate impacts of this system has been on human work itself. Robots significantly reduce the distance workers need to walk during a shift, often by several kilometers, given the scale of these warehouses. So, by removing this repetitive and physically demanding movement, both productivity and workplace safety improve. It's important that these robots do not replace humans in their system. Instead, they remove the most repetitive and injury prone tasks. Human workers still remain central, providing judgment, oversight, and flexibility where it matters. A helpful way to think about this is to view a fulfillment center as kind of a smart city. Inside the warehouse, aisles replace roads, robot replace vehicles, and inventory flow replaces traffic. AI-based scheduling replaces traffic signals. The same coordination challenges exist, just a different scale and in a controlled environment. So this brings us to the idea of fleet orchestration. So Amazon does not rely on robots being individually intelligent. No single robot is particularly smart on its own. Intelligence emerges at the system level. AI decides which robot moves first, how congestion is avoided, how safe paths are chosen, how speed is balanced against safety, and how the system recovers automatically from failures. That system level intelligence is the key takeaway here, and which I wanted to touch on. Coordination, not autonomy, is what drives performance at scale. Once you see fulfillment center as a coordinated system, it immediately would parallel to vehicle fleets or traffic systems or infrastructure. So, a very useful way to understand Amazon's ecosystem is to think of a fulfillment center as a smart city that we touched on from the previous slide. Inventory movement behaves like the traffic flow here. And instead of traffic lights, AI-based scheduling system coordinates moments across the entire space. The complexity here is obvious. Just like a city, there are congestion points, there are peak hours, unexpected disruptions, and safety constraints. And just like a city, local decisions affect the entire system. AI's role here is similar to an intelligent traffic control system. It continuously observes conditions, predicts that congestion, and adjusts the patterns so that the system should flow smoothly and safely. What's important is that intelligence is centralized. Individual robots are not making independent decisions. AI looks at the entire environment and coordinates this behavior. This is exactly the same intelligence pattern that we want to see in urban mobility. If AI can manage congestion, safety, and efficiency inside a highly constrained warehouse, the same principles would then equivocate to traffic systems, EV fleets, and city scale mobility outside. The environment changes, but the coordination problem remains the same. So the algorithm flow would still remain the same at the back end. Now that we understand this system analogy, let's look more closely at how AI actually orchestrates movement at scale. So one important point here is the language, because it reflects how these systems are actually designed. Amazon does not use AI to directly control the robots, as I pointed in the earlier slides. Neither do they do that in isolation. Instead, they use AI to orchestrate the entire fleet. No single robot is particularly intelligent on its own, but intelligence emerges, thousands of robots are coordinated, and then AI decides how the congestion would be avoided, how the safe paths are chosen, how speed would be balanced. Each of these decisions may seem small in isolation, but together they determine whether the entire system flows smoothly or breaks down. This distinction between control and orchestration is critical. Control implies micromanagement of individual agents. Orchestration focuses on coordination, prioritization, and overall system behavior. This applies directly to mobility systems. Smarter cities and EV fleets are not about heroic vehicles making perfect decisions on their own. They are about coordinated behavior across thousands and millions of agents, vehicles, chargers, signals, all of them responding to shared constraints and goals. So, when designed correctly, orchestration allows systems to be safer, efficient, and more resilient, even when individual components fail or behave unpredictably. That system level intelligence is what ultimately enables scale. A study at Amazon Automation shows that improving path planning delivered 35% more throughput, surpassing gains from adding extra robots. That alone citation should give us a quick insight. So once coordination is in place, the next question becomes how systems learn and improve over time. So one of the most important aspects that I wanted to highlight from Amazon was through their case study, how intelligence alone can dramatically improve system performance. I wanted to touch base on Sequoia and Deep Fleet. Let's start with Sequoia. So Sequoia is a AI-powered inventory system inside Amazon that uses computer vision and machine learning to sort and store items significantly faster. You will often hear that it can sort and store inventory by up to 75% faster than a human could. But the speed alone here is not a real win. The real value is predictability and efficient flow. So by reducing unnecessary movement, Sequoia lowers manual handling, reduces wasted space, and decreases energy consumed per package. Fewer movements mean fewer forklifts, fewer handoffs, and smoother operations overall. Then when we touch defleet takes this idea even further. It is a fleet level AI model that optimizes how all these robots move together. It learns from historical movement patterns inside warehouses to anticipate congestion, reduce idle time, and improve overall throughput. What's important is that defleet improves performance without adding more robots. The system behaves more efficiently simply by coordinating existing assets better. This insight generalizes directly to mobility. Smarter routing beats adding more roads. Smarter charging beats adding more charges. And intelligence allows us to extract more value from the infrastructure we already have. Another critical aspect of these systems is prediction. What AI at Amazon predicts what customers will order, where those inventories should be placed, when congestion is likely to occur, and when machines need maintenance. This predictive capability reduces last minute transport, lowers energy spikes, and smooths operations across the system. At the same time, human responsibility remains central. AI assists decision making, but it does not replace it. Humans still make the final decisions. Safety overrides always exist, and systems are designed to fail gracefully rather than catastrophically. This is the key lesson of this case study. At scale, the most important insights are not about specific algorithms, they are about the system behavior, prediction, coordination, resilience, and responsible oversight. This is what this example was supposed to highlight. With these lessons in mind, let's step back and go through what this means for mobility, electric vehicles, and daily life. Electrical vehicles are at their core electrical systems, if you think about it on a granular level. They involve batteries, power electronics, motors, and control systems. But what increasingly defines their efficiency, usability, and sustainability is intelligence layered on top of that hardware. Two vehicles with similar batteries and motors can perform very differently depending on how intelligently energy is managed. AI plays a role in deciding how power is delivered, how energy is conserved, and how the system adapts to real world conditions. Moving on. In an electrical vehicle, intelligence helps translate this raw electrical capability into practical performance. It continuously interprets signals from the battery, the environment, and the driver, uses that information to make decisions that improve the efficiency and reliability. This intelligence does not replace core electrical engineering. Instead, it amplifies it. AI allows EV systems to operate closer to their optimal limits while respecting safety, longevity, and user comfort. As electrical vehicles become more connected and more integrated with this charging infrastructure and the grid, this role of intelligence becomes even more important. EVs are no longer standalone machines. They are a part of a larger energy and mobility ecosystem. With that perspective, let's look at the specific areas inside electrical vehicles where AI makes the biggest impact. Let's break this down by looking how AI supports batteries, energy management, and vehicle behavior. So I wanted to bring together three closely related domains here: electric vehicles, traffic management, and shared mobility. While they appear different on the surface, they're connected by the same underlying intelligence patterns we have been discussing. Starting with electrical vehicles. AI and machine learning play a central role in optimizing battery management and powertrain efficiency. Adaptive control strategy continuously adjust how energy is used based on driving conditions, temperature, and usage patterns. So this helps EVs operate closer to their efficiency optimal envelope. Another critical application is predictive maintenance. Machine learning models analyze historical and real-time data to forecast battery degradation and component wear. This is especially important for EV fleets where proactive maintenance improves reliability and reduces downtime, and also lowers the total cost of ownership. As EV adoption accelerates globally, these capabilities become absolutely essential. Managing millions of EVs efficiently requires intelligence at the system level, not just better hardware, but smarter usage, charging behavior, and lifecycle planning. Then moving on to the traffic management. AI is increasingly used to reduce congestion and improve overall flow. Adaptive traffic control systems rely on real-time data from cameras, sensors, connected vehicles to adjust signal timing dynamically. Unlike fixed schedules, these systems respond continuously to actual road conditions. They route prediction and navigation systems and use machine learning to anticipate congestion before it fully forms. So, by combining historical patterns with live data, they help distribute traffic evenly across the network. Smart parking systems further reduce unnecessary driving by guiding these vehicles directly to available spaces, lowering emissions and congestion in dense areas. Finally, shared and on-demand mobility systems rely heavily on artificial intelligence. A couple of examples that I wanted to cite was adaptive signals already placed in Pittsburgh, Pennsylvania in United States have reduced the travel times by 25% in the early trials. Waze is one of Google's holding companies like Google Maps. Their algorithms have saved millions of minutes per year. Google has reported 20 to 30% travel time reduction with machine learning routing. Similarly, if you had to take ride hailing platforms like Uber or Lyft, they have been using machine learning to match riders with drivers efficiently predict arrival times, and optimize fleet utilization. So AI can not only boost battery life predictions, but it can smartly route, predict, and optimize. These systems aim to reduce empty miles while improving user experience. If we had to touch base on mobility as a service platform, they extend this idea by integrating public transport, ride hailing, and micro mobility into a single trip plan. So, in controlled environments such as campuses or selected urban zones, AI enabled shuttles and logistics pilots are already demonstrating how shared mobility can move more people in fewer vehicles. So, across all these areas, the unifying theme is optimization at scale. AI enables mobility systems to deliver higher efficiency, better safety, and improved sustainability without proportionally increasing infrastructure. So, as mobility systems scale up, they increasingly interact with energy infrastructure, which brings us to the role of AI in charging systems and power grids. Here, I wanted to bring together two important ideas: how AI is already being used in vehicles today, and how global EV adoption is accelerating in parallel, and what are the trends. So, let's start by separating two concepts that are often mixed together: driver assistance and autonomy. Today, the dominant application of AI in vehicles is advanced driver assistance systems, or ADAS, how it is acronymed. These systems focus on assisting the driver, not replacing them. Examples include safer braking, lane support, adaptive cruise control, and driver monitoring. Machine learning is used here primarily for perception, detecting vehicles, pedestrians, lane marking, and supporting safer decisions. These systems are already widespread in use. A significant portion of new vehicles today includes some level of ADAS, and some of the projections indicate that this will continue to grow over the rest of the decade. From a safety perspective, this is where AI is already delivering a real measurable impact. Autonomy, on the other hand, is about reducing or removing the need for human intervention in specific driving tasks. It is important to be clear here, right? Full autonomy is not a switch, it is a spectrum. Progress happens gradually in limited environments and under strong regulatory oversight. Most real world deployments today operate in constrained settings. They would either have fixed routes, campuses, or well mapped urban areas, and their boundaries would be fixed. So the gradual rollout reflects the fact that mobility systems are safety critical and must earn trust over time. Alongside this technology trends, we are seeing a rapid shift in vehicle electrification. EV adoption is accelerating across major markets. China currently leads both in production and adoption, while Europe and United States continue to expand their EV share. Emerging markets are also electrifying transport driven by affordability improvements. And then they have supportive policy frameworks. What this tells us is that intelligence and electrification are progressing together. Moving on. So, as the number of electrical vehicles increases, the role of AI becomes even more important.
பலசர கேட்டு எழுது.
So, the key takeaway from this slide is scale. Again, mobility systems are becoming more electric, more connected, more intelligent at the same time. AI enables these systems to operate safely, efficiently, and sustainably. So, as this adoption grows, the interaction between vehicles and energy infrastructure becomes critical, which brings us to charging systems and the power grid. So, up to this point, we have focused primarily on vehicles and mobility systems. In the next slides, we'll transition to broader environment, and how these systems operate in. Smart mobility does not exist in isolation, as we already talked about. It depends on infrastructure, roads, charging networks, power grids, buildings, and communication systems, all working together. As these systems become more connected, intelligence at the infrastructure level becomes just as important as intelligence inside vehicles. When we talk about smart cities, we are really talking about coordinated systems. Traffic, energy, public transport, and utilities all influence one another. AI and ML help these systems sense conditions, predict demand, and coordinate responses across the city. In the next few slides, we'll look at how AI is being applied to this infrastructure and urban systems to improve reliability and sustainability, while still having that layer of intelligence for the scaling. Let's start by looking at how AI supports charging infrastructure and power grid. So, this is where mobility and energy systems truly intersect. As electric vehicle adoption increases, vehicles are no longer just loads on power grid. They become active participants in the energy system. AI plays a critical role in enabling this interaction safely and efficiently. Let's start with the smart grid. AI helps balance power supply and demand for EV charging by understanding when renewable energy is abundant and when the demand is high. Instead of charging vehicles immediately, systems can schedule charging intelligently to align with cleaner and cheaper energy. This brings us to the idea of vehicle to grid, or V2G as it's acronymed. In this model, act as mobile batteries. One of the projects that I wanted to point was from the European Union. It was termed as H2020 project or Green Charge, where they used AI for this vehicle to grid concept. What they do is they can store energy when solar or wind generation is high and when appropriate, and then send this energy back to the grid during peak demand. AI manages when and how much this energy would be discharged by predicting both driving patterns and renewable energy output. These are already pilot projects where EVs help stabilize local grids, especially in areas with high rooftop solar adoption. By smoothing demand and supply, these systems make easier to integrate more renewable energy without compromising grid stability. Smart charging stations are another important piece where AI optimizes load by scheduling vehicles, deferring charging during peak periods, and then supporting dynamic pricing. This avoids overloads and reduces stress on local distribution infrastructure. AI is also used to forecast short term energy demand spikes, sometimes 5 to 15 minutes ahead. These short horizon predictions are extremely valuable because they allow grid operators to react before instability occurs, improving reliability. One of the examples is Singapore's smart traffic system adjusts signals to ease congestion. In Barcelona, traditional streetlights, along with sensor adoption, have saved 50% energy. Doppler radars and cameras on highways detect jams, triggers alternate routing in real time, is how they use this. So, beyond energy, AI also plays a major role in transportation infrastructure. Connected traffic systems use sensors and AI to coordinate traffic lights, pedestrian flows, and emergency response. So connecting back rather than being isolated intersections, the system behaves as coordinated network. Parking management systems also benefit from this. By allocating parking dynamically and guiding drivers to available spaces, cities reduce unnecessary cruising, congestion, and emissions. The key idea tying all of this together is that the entire transportation network becomes a cyber physical system. Vehicles, infrastructure, energy, and communication systems interact continuously. This is where electrical engineering, control systems, and AI converge. Concepts like load balancing, stability, reliability, and resilience move from theory into large scale real world systems. So, as infrastructure becomes more intelligent and more interconnected, questions of safety, security, and governance becomes increasingly important, which we'll address in the next slides. So, we move the discussion from mobility and infrastructure into daily life and smart homes and how AI is integrating into this. Let's start with smart cities. Cities already generate enormous amount of data from cameras, sensor, transit systems, utilities, and public services. AI allows cities to move from simply collecting data to actually using it to improve safety and the quality of life. For example, AI-driven city systems can analyze patterns across multiple data sources to improve public safety. So this includes detecting unusual activity, predicting congestion or hazards, and issuing alerts during emergency. The goal is not surveillance, but faster, more informed response. Sustainability being the major focus point. Another example would be smart waste systems that can signal when bins need to be picked up, reducing unnecessary routes, and AI can optimize public transit schedules based on demand rather than fixed timetables. Air quality sensors combined with AI models can trigger alerts or policy responses when thresholds are crossed. From a citizen's experience perspective, AI enables interactive dashboards, adaptive street lighting, and better noise and traffic management. So, this broader idea is where cities become more responsive rather than reactive. That is an emerging concept where there is this idea of digital twins. This involves creating a virtual model of a city or a part of a city that can be used to stimulate traffic changes, infrastructure upgrades, or emergency scenarios before implementing them in real world. This is still evolving and there are still pilots in place, but this is where urban planning is headed. In Los Angeles, the LAPD uses AI to analyze crime patterns for resource development deployment. Smart waste bins in Dublin use fill level sensors to optimize collection routes. AI tuned transit can feed into mass systems, as we talked about on the previous slides. Now, shifting to smart homes and buildings, we see similar intelligence patterns at a smaller scale. AI assistants can coordinate EV charging, heating and cooling inside the house, and lighting based on schedules, occupancy, and energy prices. Smart thermostat and meters learn household patterns and adjust their energy usage automatically, reducing waste without sacrificing comfort. Nest Thermostats, a Google's holding company, uses machine learning to learn occupancy patterns, saving 10 to 15% on heating bills. When combined this with solar, home batteries, and EVs, AI can manage the entire home as an integrated energy system. Predictive maintenance is another important application where ML models can detect early signs of faults or energy leaks before these failures occurs. In commercial buildings, this same intelligence improves downtime and operating costs. So AI coordinates these pieces to improve resilience, efficiency, and the experience. As these systems become more connected and data driven, we definitely need to question governance, security, and trust as they become central to this. So this slide brings together the environmental dimension of everything we've discussed so far. Let's start with emissions and efficiency. Vehicle electrification has a direct and a measurable impact on carbon emissions. Global studies show that widespread EV adoption can avoid the order of gigatons of CO2 emissions over the coming decades. even when we account for full life cycle emissions rather than just tailpipe effects. Even non electric cars emit less CO2 with AI guided traffic. Battery electric vehicles already emit significantly less CO2 over their lifetime compared to internal combustion vehicles. And that gap continues to widen as electricity grids become cleaner. This makes EVs not just a transportation shift, but a structural change in how energy and mobility interact. AI plays an important supporting role here. Smarter routing, adaptive traffic control, and reduced congestion means less stop and go driving. That translates into lower fuel consumption and emissions, even for hybrid and conventional vehicles. At a system level, the combination of AI and electrification also reduces dependence on oil. So, oil displacement becomes meaningful at a global scale, affecting energy security as well as emissions. The second half focuses on renewable energy integration, which is where AI becomes essential. Renewable energy sources like solar and wind are variable by nature. So AI here can help forecast renewable energy generation and align EV charging with periods of high availability. Instead of treating EVs as a problem for the grid, they become a flexible resource. For example, an AI scheduler can delay charging until excess solar or wind energy is available, maximizing the use of clean electricity without any action from the driver. Time of use pricing combined with smart meter reinforces this behavior automatically. Vehicle to grid systems extends this further. EV batteries can act as distributed energy storage, smoothing fluctuations in renewable supply. This is why intelligence is not optional in sustainable mobility systems. It is what allows environmental benefits to scale reliably. So, as these systems grow in scale and importance, governance, security, and trust become central. We now are going to look into the three different aspects. Everything that we discussed so far, how this translates in mobility systems. So, in mobility systems, the physical world has consequences. Errors are not abstract, they cost energy, damage infrastructure, and in worst cases, cost lives. That's why AI in mobility is fundamentally important from AI in purely digital domains. Smart mobility systems are cyber physical systems. They tightly integrate computation, communication, and physical processes. One of the examples was the automotive sector was hit by a torrent of cyber attacks in 2024, from ransomware locking factories to breaches of consumer data. So, an autonomous vehicle, for example, combines AI models with sensors, actuators, braking systems, and steering. Decisions are made by software immediately, and that affect the physical world. The same is true on city level, traffic level, interconnected infrastructure, and even drone or delivery systems. They all operate as coupled digital and physical systems. That is why concepts like digital twins are becoming important. They allow cities to stimulate changes and stress test scenarios virtually before applying them in real world. Because physical consequences are involved, safety margins matter. These systems must be designed to fail safely, degrade gracefully, and prioritize human life above optimization. Data is a critical enabler for AI, but it also introduces privacy challenges. Vehicles collect sensitive information such as location, driving behavior, and sometimes biometric indicators. So, as awareness grows, users are becoming more cautious about how their data is collected and used. We already see evidence of this in declining adoption of certain connected services due to privacy concerns. This reinforces the importance of anonymization, edge processing, and giving users clear control over what data is shared and for what purpose. Trust becomes a prerequisite for adoption. Cybersecurity adds another layer of complexity. Connected vehicles and infrastructure are potential targets for attacks. Vulnerabilities can arise through wireless interfaces, infotainment systems, third party software, and supply chains. So, the impact of a successful attack in mobility systems can be severe and ranging from not just data breaches, but to safety critical failures. This makes cybersecurity an engineering requirement, not an afterthought. Mitigation strategies include secure by design architectures, hardware security modules, encryption, continuous monitoring, and secure over the air updates. Standards and governance frameworks play a critical role in ensuring consistency and accountability. Some of the examples already in place are they are emerging worldwide. There is U, US has already implemented NHTSA guidance, while Japan has their own JSAC. So the key message is responsibility. As engineers, researchers, educators, we are building mobility systems. We definitely need to design them for safety, privacy, security. With that perspective, I'll close with a few takeaways on what this means for education, research, and next generation of engineers. Up to now, we have talked about what AI and ML can do for mobility in energy and cities. What we are going to see is how this system should be designed, deployed, and governed responsibly. Mobility systems operate in public spaces. They affect safety, access, fairness, and trust. That means ethical considerations are not optional, they are a requirement. So we are shaping the systems that people rely on every day, often without thinking about them. I'll briefly outline what responsible AI looks like in practice for mobility systems. When AI is applied to mobility, we are no longer working in purely digital environment. These systems operate in public spaces and access influence our safety and trust. That changes the responsibility that engineers carry. Fairness becomes an engineering concern. Mobility systems shape how people move through cities. If an AI based routing or traffic optimization system consistently deprioritizes certain neighborhoods, that becomes a form of bias, even if it is never intended. Responsible design requires actively testing for these effects and correcting them. Safety and liability are equally critical. When AI systems influence braking, steering, routing, accountability must be clear. Engineers need to know where human responsibility ends and automated assistance begins. That is why human oversight, fallback mechanism, and clear responsibility boundaries remain essential. Transparency is one of the pillars. When AI systems read out drivers, prioritize traffic, or influence charging behavior, users and operators should be able to understand why those decisions occur. Explainability is not only about trust, it's about debugging, auditing, and improving system performance over time. Responsible design means avoiding unnecessary computation, choosing efficient models, and aligning AI usage with sustainability goals rather than undermining them. That means stricter expectations around testing, documentations, monitoring, and human oversight before deployment. The intention is not to slow innovation, but to ensure that safety critical systems behave predictably and responsibly at scale. Studies predict 39% of current jobs will be disrupted by 2030. 39% of workers expect skills to be outdated by 2030. But on the other hand, if we look at that spectrum, the public acceptance, one might say that surveys still show 60% of people don't trust self driving cars. So there needs to be a balance. An important development here is an idea of regulatory sandboxes. These allow new mobility technologies to be tested in a controlled environment under supervision. This recognizes that innovation and governance must evolve together. Broader message is balance. Responsible AI in mobility is not about choosing between innovation and regulation. It is about building systems that earn trust, protect people, and scale safely over time. So, as powerful as these systems are, it is important to be honest about the challenges ahead. From a technical standpoint, mobility is one of the hardest environments for AI. The edge cases matter. Poor weather, sensor degradation, unexpected human behavior, infrastructure failure can all stress these systems. Full autonomy is difficult not because progress is slow, but because reliability must be extremely high under all conditions. These are also infrastructure challenges. Intelligent mobility depends on charging networks, reliable connectivity, and modern traffic systems. The major challenge not only being on the technical side, but also the challenge is skills. Many roles will change as AI becomes more embedded in mobility and energy system. This does not mean fewer opportunities, but does mean different ones. Skills in data, systems thinking, domain knowledge, they become increasingly important. This creates a strong need for continuous learning and reskilling. Public acceptance is equally critical. AI is already helping reduce congestion, lower emissions, improve safety, and make better use of existing infrastructure. Some ideas will arrive sooner than others, and not all will scale immediately. Readiness matters as much as innovation. The core message here is AI is a tool, a powerful one. When applied thoughtfully, it helps build greener and smarter mobility systems. But with that power comes responsibility. Security, privacy, ethics, and governance are not constraints. They are what allow innovation to scale safely. This is an opportunity to shape how the next generation thinks about systems. Integrating AI, data, and domain knowledge into engineering education is no longer optional. For students, this should be an invitation. The future of mobility will be built by people who understand both technology and the context behind it. Those who can connect AI with real world constraints will lead. As we wrap up, I want to leave you with one simple thought. Artificial intelligence and machine learning are no longer separate subjects or standalone tools. They are becoming the connective layer across electrical engineering, software engineering, control systems, energy infrastructure, transportation, and society itself. In mobility and electric vehicles, hardware enables capability, but it is the software and intelligence that increasingly define performance, safety, and sustainability. They are the core engineering requirements in any system that operate in physical world and affect people's lives. Thank you for your attention, and I'd be happy to take questions or hear your perspectives. Any questions from anybody's end?
If anyone having questions, please unmute yourself or uh, write your question in chat box.
आला की सक्सेसफुल म्हणून अटेम्प्ट डिलिव्हरी अटेम्प्ट फॉर इज सक्सेसफुल असं आलंय.
Sorry, could you repeat your question, Bharat sir?
Sir, I like to appreciate you for one line. You told AI is not going to replace humans, but it needs skills. Yes, but
Yes.
that is I like very much, and I came to learn from you that AI is going to need skills. Okay.
Yes. Thank you, sir. I wanted to make that distinction clear because Amazon has 1.5 million people that work for them, right? When we started working on AI projects, we started building AI internally. There were a lot of concerns of we are going to write out our own jobs, but that's what needs to be speculated and separated. You need to work on different skill set and still work in your own roles because AI will always need oversight. So thank you, sir. Any other questions?
Hello, sir.
Hello, ma'am. Yes.
Huh. Sir, I would like to know in Amazon, which all
Yes.
sections have the AI implementation?
So, ma'am, all the sections in Amazon, all the departments in Amazon have
Uh,
AI enabled currently.
uh,
What Amazon did was, I'm going to take you back a little. So
okay, sir.
when artificial intelligence was still churning, the big companies, right? Apple, Amazon, Google, Microsoft, they all started to work on their own AI. So Amazon built their own AI system, which is called Q. We don't use ChatGPT or we don't use any other third-party systems. Q is not available to anybody else other than Amazon. So when we talk about Q, what we did was we had more than 148 different agents built inside of Amazon, named Cedric, Cortana. We built 148 agents and then we boiled down to Q. We integrated all of them. So if it is software ordering, if it is routing, if it is warehouse routing, if it is robot routing, if it is order scheduling, or if it is internal usage, right? Like I have to talk to other person. We have AI embedded in everything today. Even if I'm writing email, it's integrated now. So right from writing an email to you getting your own order, there is a bit of artificial intelligence that is used today.
Thank you, sir. Are there
Yeah,
any
absolutely.
different standards of ethical considerations for the implementation for various departments, sir, in your
Yes.
Amazon?
Yes, they vary. So Amazon is known for their security standards, ma'am. When we
Okay,
build something, we build something in say 6 months, okay? But the security review takes 2 years to pass that.
okay,
So
okay.
that's how complex the security reviews are inside of Amazon. And everything depends on your own tenets. So when you build a project, you have tenets and abstracts of how you build the projects, what are your considerations, and that is what will define the security reviews later. Now, when it comes to governance and ethical considerations, there were a lot at the start that were not looked at correctly. And that's why I
Okay.
touched based on that. Currently, majority of our times when we build projects goes on security and governance, how that data is handled, what kind of data is handled by AI, and what it will do. For example, I'll just give you a short example. I have my own agent that I've built from scratch. What it'll do is it'll auto reply to emails, it'll go see what the tasks are, and I have 7 different teams that report to me from 7 different parts of the world. So it will keep operating 24 hours because some I when I sleep, the script still goes on. It's an AI agent. So what happened was when it stuck a hurdle, right? It bypassed that. It wrote a different agent. There was a different instance generated, and it bypassed Amazon's security lines, and then it did what it had to do. So that is why security and governance play a key role when we build this kind of things. Hope that is clear.
Yes, sir.
Yeah.
So any kind of problems that were come across by you people
Mhm.
from the customer side because of AI implementation?
A lot of problems, ma'am. We deal with at least a few hundred problems. At the very start, there were a lot of issues uh, where people didn't understand how exactly the process was broken down. Because if you think about AI implementation, it is breaking the process down into parts, understanding that process, and then reiterating it. We had major problems from vendors. Incorrect orders were being created, incorrect deliveries were being delivered, and a lot of deliveries we lost the products because in US, Europe, you actually don't get back the product once it is delivered due to privacy concerns. So a lot of software problems, hardware problems, procurement problems came up, and we had to have this downtime. So that's why we said the twin city kind of a thing, right? We have sandboxes now. We play in sandboxes. We make sure everything is it breaks gracefully if it breaks, because you can't actually build a system that is unbreakable, right? And then you implement it at scale.
Thank you very much, sir.
Absolutely.
Yeah.
Any other questions?
Sir, one more question.
Sure.
Sir, with respect to your Amazon only, I'm talking
Okay.
about robustness now. Now, from where it has started, this robustness parameter, now where it has come as on today.
Could you extend the question a little, ma'am?
Now, how best it has performed over the period of say 10 to 50, 10 years. How it has
Which
improved,
one?
sir?
Which one are you
Your
talking about?
AI implementations in various
Sure.
departments.
Sectors. Yeah. So one of the examples that I would like to give is so when a person orders something, right? Imagine this: you place an order in the back end, it is routed to the department, and then it is routed to the correct warehouse for logistical shipping and then labeling and all of that part, right? So when that order was generated, we had AI look through how it would be routed correctly, which warehouse would be routed correctly, depending on thousand other orders that were in that basically in that geographical area, but not specifically closer to your warehouse. What Amazon does is Amazon has warehouses next to airports. And usually, if say you're ordering from Bangalore, right, and there is a warehouse right next to the Bangalore airport, there are 90% chances your was going to be done by that Bangalore warehouse. Now, when we go back and look at every minute, Amazon receives millions of orders. And how that is routed is again algorithms and AI. That is number one. Number two is say that order is routed through a warehouse, right? And it goes through a robot. Now, what happens is we built our own robots, which are big in size. They're three times the size you see a normal robot, cleaning robot in any household. And what it does is we've translated all the warehouse logistics into matrix. So each rack is basically a collection of rows and columns. So you say you order something and it's basically in row G, column F. What that robot will do now is AI will help that robot to understand which rack it is, what orientation that rack needs to be at. And what it will do is the robot will go on the bottom, pick that up, the whole rack, and then bring it and turn it so that that column F is visible to a person sitting there or a robot hand that we built. And that robot hand will just go grab it and throw it in a box. And again, the process is automated. Where and how that is routed, again, that uses AI. How many boxes are routed, how those boxes are routed. So end to end, we removed the human interaction from that loop. So this was the project that we built over the past 8 years, where no human is needed anymore if an order needs to be fulfilled from point A to point Z.
Wonderful, sir. Thank you for giving such a great information about AI implementation in Amazon, how it is
Yeah,
working
absolutely.
so fast for all
Absolutely.
the customers.
Yes.
Thank you, sir. Thank you.
Absolutely. Any other questions?
I think No questions are pending now, sir.
Okay.
I'm here to propose the vote of thanks. Thank you, Mr. Darshan Karnawat, sir, for your thoughtful insights regarding the AI usage in replacing mobility overall. Uh, by showcasing the real-time examples at Amazon, how it is working. Also, the major takeaway points like how AI is boosting efficiency and sustainability, its real-world impact, and how the human responsibly should practice the AI. So, once again, from the organization, I would like to thank you for your thoughtful session and your time. Thank you, sir.
Thank you. Thank you, everyone. Appreciate your time.
Thank you, sir. Thank you, sir.